Let's understand in this video the concept of differentiability. So, differentiability. First of all, what is this word? It comes from the word to differentiate. And what is differentiation about? It's about taking derivatives. So intuitively, it's all about, are we able to take the derivative of the function? Is there an actual slope of the graph? And let's work through an example and see how it looks like. So for instance, what if we have such a function? So we have y and we have x, and the function goes like that. And we want to know if the function is differentiable at this point of x. So this would be our x value that we're interested in. That would be the y value corresponding to it, or we call it f of x. And now, how can we prove if the function is differentiable or not? Remember, what is a derivative? What is f derivative of x? How did we write it in 2 weeks ago? We had this limit which we call the Newton quotient, right? And what it means is that if we take our function, so we have f of x plus h minus f of x divided by h. What this literally means is that what happens when we slightly take a value above our function, so x plus h. Let's put it here, x, and we increase x by h. Well, we would have as a result f of x plus h. This is where it would look like f of x plus h. And now the limit when h approaches 0 means that the difference between this value and x plus h has to be very, very small. It's not going to be literally 0, but when x increases by 0.001, for instance, how does y increase? So we call this an instantaneous rate of change. What was the derivative? That's the change in y relative to change in x. And indeed, we can see it on the graph. F of x plus h, that's this y value, minus f of x, which is the following y value. So we have our delta y over here. And what is h? H is the difference between x plus h and x, because we increment x by h. So this is our delta x. And literally, delta y over delta x gives us our derivative. And the derivative is the slope of the tangent line to this point. And the whole notion about h approaching 0 is just the fact that we are getting the difference between these 2 points as small as possible to see what the derivative is here. So visually we can see that the function is differentiable. Our slope, it exists, it's over here, it's defined. But how can we prove it with this limit? Well, if we get to that point, if we get to that value of what this limit approaches, we can see that we approach the same value from this side and from the other side. And this is what matters for this concept, that if the limit of h approaching 0 from the negative side, and what does that mean? That means that what happens if we have x plus a negative value of h, so minus h. Well, again, what value are we approaching? That's the question, because either we take a value to the right of our x or to the left of our x. If we decrement it, if we literally minimize that difference between x and x plus h, we will tend to approach the same point. We will tend to approach this value. So if the limit as h comes from the left side, that's why you say it's 0 from the negative side, because 0 from the negative side, it means that the difference between x and the other point will be x minus 0.0001. So it would be a very, very small difference. Of this whole thing of f of x plus h minus f of x divided by h has to be equal to the limit when x approaches from the other side, when x go from here, when our difference between x and the other value is a very small positive number, it's 0.0001. And we get to the same point, f of x plus h minus f of x divided by h. So if this holds, if our limit approaches the same value, it means we're approaching the same point on the tangent line, which means our slope is defined as this at this point. and that's why our function is differentiable. We can take the derivative at that point. But look at this example in contrast, and always when you look at concepts, at new concepts, study them in contrast, study them with differences, because when you understand differences, it all makes sense. So let me zoom out and draw something right next to it. Let's take it over here so we can see what happens if this is not the case. If we still have an xy value, an xy axis, but what if the function now looks something like that? What if it looks, it goes here, it has a gap, and then it starts from here onwards, and this is our f of x. And we would like to know the same thing. What is the limit? What is the derivative at this point? Well, we can see that there's going to be something different, because the function itself has this following value, f of x. You see, the colored point is what the actual function takes the value for. Here is undefined, here is a gap. So that means that if we approach x, if we give values closer and closer to x from this side, look what happens. If we give values closer and closer to x from the left side, we are approaching this gap. But if we give values of the function from the right side, if x takes values from the positive side, values slightly higher than x, when it approaches 0 from the positive side, when the difference between x and x plus h is slightly positive, we are approaching this following value, we are approaching this point, and we can see that they are different values. So the limit, when we approach from the negative side of f of x plus h minus f of x divided by h, is not the same as the limit when you approach from the positive side of f of x plus h minus f of x divided by h. So f of x plus h minus f of x divided by h. And because they are not equal, it's not a differentiable function. And indeed, how can we draw a slope here if we don't know which values are we actually taking? Is it over here or is it over there? So that's the intuition behind it. I hope this graph makes more or less sense. And in the next video, we're actually going to cover continuity.